what time do we get out? Like 11:45?
Yeah.
So it'll be up usually by 2 or 3. Okay, so I gotta remember how to teach. It's been a while. Okay, so we're going to start with concepts of velocity, position, and acceleration. Should be pretty familiar to most of you. You should have done a little bit of it in Calc 1, and maybe in physics if you've had a physics course. Thank you.
Yeah.
So let's imagine the most boring of all movements, straight line. So you've got a particle, a car, whatever. It's just moving in a straight line. It might be able to change directions and go exactly backwards, but movement is on a straight line. Okay? So that's kind of the simplest motion problem we can imagine. And we use S to represent the position of the object at a particular time. And so here we have S of A, we have S of B, so you can think of that S of A as the initial position. It's a number on a number line. S of B is the terminal or final position. It's a number on the number line. And if you take the difference and you get a positive number, then you have positive displacement. So if you end up to the right of where you started, positive displacement. On the other hand, if you start at A, S of A is your position at time A. S of B is your position at time B. If you end up to the right, to the left of where you started, if you started to the right and you ended up to the left, then you have negative displacement. Both those scenarios do have distance traveled. Distance traveled is always non-negative, 0 or positive. But displacement can be positive or negative. Or it could be 0. And if you drive to school and you drive home, your displacement is 0. But your distance traveled is certainly not 0. So we want to turn that idea into math. You've already done it. You did it in Calc 1. We want to integrate the velocity to get displacement. Well, velocity is the rate of change in position. It's S prime. And we know how to integrate this from Calc 1. If you're integrating a derivative, you take the antiderivative, so you'll take S and you form the difference of your antiderivative at the upper end point and the lower end point, right? That should be super familiar. It's called a definite integral. So you take your antiderivative at the upper limit of integration and subtract off the antiderivative at the lower limit of integration. That's displacement. So we didn't even have to do anything. The definite integral, if you definitely integrate velocity, you get displacement right out of the gate. So we already have math to do that. So if we know our velocity function, integrate it, plug in your endpoints, take the difference, we have displacement. So not too bad. Then we can think of this very visually. So let's come here. So we're imagining that curve as the velocity curve. So we're still dealing with just motion on a line. It's a little ping pong ball going back and forth on a line. So this is the velocity of the particle or the little ball or whatever, your car. If the velocity is positive, you're moving to the right on that number line. If the velocity is negative, you're moving to the left on that number line. And when we think about the definite integral from A to B, the geometric interpretation of the definite integral is that you take the area trapped above, in this case the t-axis, and you take the area below, area is positive, and you take the difference. So displacement is area 1 minus area 2. That's going to give us displacement. Okay. So sometimes they'll talk about signed area. If you talk about signed area, then this is a negative number. If you're using the expression signed area. Typically, you just think of upper area minus lower area. That's going to give us our displacement. And if we want the distance traveled is going to be the sum of the two areas. it's going to be the integration, the definite integral of the speed. If you take the absolute value of velocity, you get speed. And if you integrate speed, you get distance. So here's a picture. If we take the absolute value of this velocity function, it takes the negative piece and rotates it to the top, and now everything's non-negative. The sum of those two is going to give us our total distance traveled. Now remember, here's one of those algebra things. The function that you're staring at right here, this is an absolute value function. There's no antiderivative for an absolute value function, typically, unless it's a special case. When you have an absolute value function, the function is piecewise defined, and if you were to integrate a piecewise defined function, you integrate each piece. Right, so you can't just integrate this with the absolute value symbol. There's no antiderivative for the absolute value symbol. You would have to turn your absolute value function into, you usually use the curly brace, and you've got your two different pieces of the function, or maybe there's more. And then you integrate each piece on the appropriate AB, the appropriate interval from your t-axis. Okay, so let's stick with the geometric interpretation of stuff. So once again, we've got velocity shown here, and we have units this time. A lot of times in math, we're not dealing with units. We leave that to the physics classes, but when they do have units, we need to put them in the answer. So we have this situation down here, seconds in meters, that's velocity. So we want to answer these questions. So let's start with A. So it says, on what time intervals, on what intervals is the object moving in the negative direction? Okay, so for A, moving in the negative direction. Someone give us a time interval?
2 to 4.
2 to 4. And the other one is 6 to 8. Yeah. So 2 to 4, definitely moving in the negative direction. Do we include the endpoints or not include the endpoints?
Not include, we do not.
We do not include because at those endpoints, what is the velocity?
0.
0, so the thing's not moving, whether it's a ball or a particle or a whatever. So there and here are the two intervals where the motion is to the left. The motion is negative. It's in the negative direction. All right. What is the displacement of the object? We don't have a good symbol for displacement, unfortunately. Like we do for distance, a lot of times we use S. But for displacement, they don't really give us a good letter. So I'll just call it DISP for displacement. So 2 to 6, displacement. So we're looking over here. We're on the interval 2 to 6. What's our displacement going to be? 2, right? So the upper area minus the lower area. That's displacement if you're looking at it geometrically. So geometrically, we're going to do 6 minus 4, 2, and the units were meters. So our displacement will be 2 meters. What would the distance traveled be from 2 to 6?
10.
10. Yeah, 10 meters. All right, so part C says, what is the total distance traveled from 0 to 6? So we're going to go 0 to 6 now. So start there, go all the way over to 6. And it's asking for distance traveled from 0 to 6. So distance traveled is going to be the sum of the areas. So it's going to be 3 plus 4 plus 6. So we're going to get 13 meters. All right, part D says, what is the displacement 0 to 8? So displacement 0 to 8 is going to be?
Negative 9.
Negative 9. So we add this up, we get 18. We add that up, we get 9. We do upper minus lower, so we're going to get negative 9. And that's also meters. So describe the position of the object relative to its initial position after 8 seconds.
9 meters to the left where it started.
Yeah. So this is a super important subtle point. We have no idea where we started. Right? We don't know the position at time 0. We don't know the initial position. Right? So all we can say is that we are finishing 9 meters to the left of the initial position. So we would need that initial position. So 9 meters left of initial position. Yeah, so does that make sense to everyone? So we don't know where we started. If they told us we start at 2 on the number line, then we're going to finish at -7. But they didn't, so all we can say is this geometric type of answer. All right, so here is a little summary of some of the important things. So position is denoted S of t. Velocity is the rate of change of position. Displacement, S of b minus S of a, which is just the definition of a definite integral. And then distance traveled is the integral on that interval of the speed. So here's what we just talked about. So here we want to predict where the object will be at some t value. And so what we need to know is the displacement on the interval plus the starting position. So the definite integral, we just saw that the definite integral gives you the displacement on that interval. Right, so this right here is going to give us displacement, but we need to know where we're displacing from. So S of 0 says, OK, we're going to start here at 2. And then whatever the displacement is, we're going to go left or right depending on whether it's positive or negative. Now, another thing that's a little different than the definite integral we just looked at is that there's a t here. Really important subtle point is that this object right here is a function of t. That is not a number. That is a function. Notice, if you use a definite integral with numeric limits of integration, if you integrate from 0 to 2, say x cubed, this is a number. This is not a function. That letter in there is called a dummy variable because it's not really a variable. This is just a placeholder. If you integrate this, you get x to the 4 over 4 from 0 to 2. You plug in the 2, and you get 16 over 4, which is 4. You blah, 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 blah. Right, so this object is a number. Totally different when that limit of integration is a variable. So if we were to integrate, let's compare. So if we integrate 0 to t x, well, let's just stick with x cubed. Now, you can't have this letter and that letter being the same. So sometimes we're going to have to change this x to something else because you want to put a t in there for some reason. You just have to make sure that these letters are different. So we still get the antiderivative same way, blah, blah, blah. But notice that here we end up with t to the 4 over 4 plus 0. You subtract off 0. So this right here is a number. It's a constant. This right here is a function. FCN for function. So just be aware of that. When you see a letter in the limit of integration, it means you're dealing with a function, not a scalar. So scalar, constant, those are all synonymous. Number, scalar, constant. So very different. So this is what we were just talking about with that last example, that we found the displacement on that time interval, but we didn't know where we were displacing from, so all we could say was 9 units to the left, 9 meters to the left. So let's try this.
Hello, how are you?
So we're given a velocity function. We want to find the displacement. So we know we just integrate. But we have this extra nuance. So it says we've got our velocity function, and we have t measured in meters per second. Oh, this isn't that. This isn't as interesting as I thought it was going to be at first. They give us the endpoints here. So we do just a regular definite integral. It's not asking us, so displacement from velocity. We're going to do this in 2 ways. Let's do this first. So let's assume that we want displacement as a function. Let's assume we want it as a function, not just the displacement over that time interval. These instructions are a little vague. So there's two questions that we could be asked. We could be asked, what is the displacement function over this interval? We could also be asked, what is the displacement on this interval, the total displacement from 0 to 3? So those are two slightly different questions. So let's go with this more general question first. So if we wanted to find this more general answer, we would set it up like this. And here's a good place where I just told you we can't have the same letter, so I'm going to put an x in here instead of a t. The function is given to us with a t, but we can't have a t there and a t in the limit of integration, so we're going to do it separately. So we do that. Okay. So the only issue here is that they don't tell us what s of 0 is, so we're only going to be able to leave this as a little bit ambiguous, kind of like that problem we saw just a moment ago. Now we do our integration. We add 1 to the exponent, divide by the new exponent. This is called the power rule. Add 1 to the exponent, get a 2. Divide by the 2, we get a 3. And this is going to go from 0 to t. And then if we plug in, we still don't know what s of 0 is in this particular case. So we're just going to plug in the t here. We get t cubed.
Would that be the 3x squared or 3x?
Yes, thank you. Thank you, thank you. And that'll be all we could do if we wanted to answer the more general thing. Yeah, if I make some silly algebra, tell me. Ask. So that's all we could do in this case. Now, if we want the displacement on the total interval, then we're just going to do numeric integration right from the start. We don't need to put an x in here because there's not a letter that's being used in the limit of integration. So we can just do pure, regular numeric integration. OK, so same type of antiderivative. We add 1 to the exponent, divide by the new exponent, so we get t cubed. Add 1 to the exponent, giving us t squared. Divide by the 2, and we get a 3. And this would go 0 to 3. Plug in the 3, we get 27 minus 27. Okay. And then minus 0. So we would end up with 0 as our displacement. So this just illustrates again that if we want to know the exact position, we do need to know s of 0, which we don't know that here. So with the second one, what kind of function is that second function? We call that an exponential function. And is it an exponential growth or exponential decay? Exponential decay, because that exponent is negative. T is not negative, so this exponent's always going to be negative, unless it's 0. But it's non-negative. The exponent is non-positive. The exponent is negative. So in your mind, you should be thinking of this ski slope thing. You're going down. It's exponential decay. So do you see, if we have an exponential decay, that the distance traveled and the displacement would have to be the same? Do you see that? So what we've noticed so far is if we have our t-axis, in order to have movement to the left, the velocity curve would have to dip below the t-axis, right? You have to do the upper area minus the lower area. But with an exponential decay like this that's not shifted, this is always above the t-axis, right? So it's never dipping below, so we never are moving to the left. The motion is always to the right. So the distance and the displacement has to be the same. No choice there. Okay. So in your mind, now exponential functions are super important. So you don't have to graph this exponential function, but I am going to, because I have noticed lately, especially, that the graphing of exponential functions is not as airtight as it should be. Everybody clear that there's no t-intercept? Right? That never can equal 0. e to any power is positive, a positive number. E to the negative 5 million, e to the positive 5 million, whatever. It's always positive. Might be super tiny, but it's positive. And there is an intercept. When we plug in t equals 0, what do we get for our intercept? 50. Right? E to the 0 is 1. 1 times 50 is 50, so that's our v-intercept. And that is at 0. And I'm just going to put a dot there because we're going 0 to 4. And this is obviously not to scale. There's 4. If you plug in 4, e to the negative 8 is a tiny number. Very tiny. Multiply by 50, it shrinks the 50. It's a small number still. We don't care what the actual value is. This is what you should be seeing, though. And that's an exponential decay. Never is going to cross the t-axis. There is an intercept, though, a vertical axis intercept. OK. Didn't need the graph here, but it's also always helpful. So the displacement in this case, let's just do the total displacement since we don't know what s of 0 is, so it's kind of a moot point at this moment. So if we want the displacement on this time interval, 0 to 4, we're going to integrate this function, and we are going to use the technique that you learned in the last 2 weeks of Calc 1. What is that very last integration technique that you learned that's so fresh in your mind because it was so recent and you were so attentive that last week at Calc 1?
It's been U sub.
Say that again?
U sub.
U sub. U sub. U sub. Most important integration technique known to man. Happens all the time, U sub. Now, we are going to do U sub the way you learned it. And then I'm going to teach you a different way to do U sub when we have a particular quality to the substitution. When you are doing U sub, most of the time your U substitution is the exponent, the inside of a square root, the inside of a trig function. Right? You just drill inside, and it's usually whatever that innermost function is. So if we're doing traditional U sub here, we are going to let u equal negative 2t, and then we're going to take the derivative and get this derivative statement there. Now, let me put a middle step in here. So in Calc 1, the first thing you learned was this, that this function is a function of t. You can differentiate the dependent variable with respect to the independent variable, and you get that. And then kind of they just tell you that, oh, yeah, du and dt can be separated. They're both they're variables in their own right. And when you're doing U sub, you want to get it down here so you can turn the dt into a du. And there's different ways to do this. Most of the time, you don't even write this stuff down, but you can. So you can isolate the dt. So what our goal is to turn all the t's into u's. Can't have a mixed match of variables in there. Can't have a t and a u, so you have to have everything matching. So we come back over here. We can factor out the 50 right away if we want. We can be patient and wait. It does not matter. It's your choice, really. This is going to be e to the u, because u is negative 2t. And then the dt part gets replaced with du divided by negative 2. You can write it in here for a moment if you want, but you know it's going to come to the front. You could just write it in the front right away. You'll learn efficiencies as we go. The limits are not 0 and 4 now because we switched to u. So we switch to u. We come up here. This substitution step right here, this is our roadmap. That's how we exchange t's for u's.
Is that a multiplication dot right there between the e to the power of u and the du over?
Yes, that's a multiplication dot. Yes.
Gotcha.
Which you can, or you all know. You don't need a dot. You can put a dot. You don't have to put a dot. You can put parentheses. We have so many ways to put multiplication. It's a little head spinning. So this up here is how we exchange t's for u's. If we have to turn these t values into u values, we come here and say, hey, t is 0. Plug t equals 0 in there, and we get u equals 0. Take t equals 4, plug it in there, and we get u is equal to -8. So now we've got a new variable, u. We've got our limits of integration reflecting our new variable. And we just integrate. Let's do this very slowly. 50 divided by -2 is -25. We come out, and so we're dealing with this. Antiderivative for an exponential function.
The same thing.
It's the craziest function of them all. It is its own derivative. It is its own integral. You know, there might be some constant manipulation if necessary, but not in this case. A basic exponential, it is its own derivative. It is its own rate of change. Its own integral. Now, another thing you could do here, generally when you look at the interval that you're integrating over, generally you sort of like it being left to right, generally. But when you look at this interval, it's going the other way. So you could switch this if you wanted it to be sort of left to right. And what would we do if I just said, hey, I want this interval to be oriented in the more traditional sense? What would I have to do to make that true?
You multiply by -1.
We can multiply by -1. If you swap the limits of integration, the effect is to change the outcome by a factor of -1. So we would put a -1 out in front here. I'll put these in parentheses. So we could do that. In practice, you know, we would just flip it and then change that sign to a positive. All right, so now we're at this stage. Now we're good to go. Integral of the exponential is itself. So we get e to the u from -8 to 0. Now we're doing just our regular fundamental theorem of calculus, saying it's going to be 25 multiplied by the antiderivative at 0. E to the 0 is 1, minus the antiderivative at the lower limit of integration, which is -8. So that's going to be minus e to the -8. That is our answer. Is that a positive number? Is that a negative number?
Positive.
Positive. Better be positive. That curve was above the t-axis. That number right there, e to the -8, is tiny, tiny, tiny. So 1 minus tiny, tiny, tiny is still positive. All right, so there is what you learned in Calc 1. Here is how we're going to do it in Calc 2. I call this the reverse chain rule. And it's important to call out because it happens so much. I want you to look right here. All we did to get this coefficient was take that coefficient there and divide it into the 50. If your substitution is linear, you can bypass all of these steps and use the reverse chain rule. Let's remind ourselves what the chain rule is for a moment. Remember chain rule. If you have a function, say y equals e to the 5x, what is the derivative of e to the 5x? The derivative of an exponential.
E to the 5x times the derivative of 5x.
So we're going to get 5e to the 5x, right? The derivative of an exponential is itself multiplied by the derivative of the exponent. That's chain rule. Reverse chain rule, instead of multiplying by the 5, we divide by the 5. Quick example here. If we were going to integrate e to the 5x, instead of differentiating it, the integral, or the derivative, of an exponential starts with itself. So we just write down the function first. If we were differentiating, we would multiply by the derivative of the exponent. If we're integrating, we divide by the derivative of the exponent. And because we're integrating here, an indefinite integral, we would have to put a plus c. Way faster. So now let's get to our problem again. Let's do our problem again. So our problem said the integral from 0 to 4 of 50e to the negative 2t dt. Here's how we do it with RCR, reverse chain. We are going to do this like 1,000 times this semester. So it's really, if you had to do that 1,000 times versus what we're about to do 1,000 times, you're going to love the reverse chain rule. This just says, okay, the 50 comes out. 50 is out in front. The integral of an exponential is itself. So we just write it down again. And then we say, oh, we can use RCR because it's linear. This is linear. This exponent's linear. The derivative of it is negative 2. And then we go 0 to 4. All right, so that gives us negative 25 multiplied by, so that constant part, I'm going to sort of think of that sitting out in front. And then we plug in the 4. We get e to the negative 8 minus e to the 0. E to the 0 is 1. We have that. And that's the same answer. If you take the minus sign and you distribute it in, you'd have that. Both are the same answer. Both are positive numbers. But very concise with RCR. Long-winded with traditional U sub. So we will be using RCR anytime we have a linear function. So let's take a break. We'll take a break somewhere around, the 10:30, 10:35. We'll take our break right now. Take a 10-minute break. And if you have questions during the break, I will answer them. All right, let's pause that recording. Fun. Doing some integration. Do some more integration. I want to do a couple quick examples. So this new idea of the reverse chain rule. In this class, we are calling it the reverse chain rule. And just a few quick examples here on that. So let's suppose we have the integral of, so you all can start doing these as I write them. I'm just going to write 3 trivial examples that, well, hopefully they'll become trivial, is the idea. We'll do. Okay. So like I said, when you go to do U sub, you generally are picking for your substitution the angle, the exponent, or whatever's inside the radical, the radicand. So those would be your substitution options. All 3 of those are linear. There's no quadratic. There's the substitution piece. Right? Inside here is linear. Up here is linear. Inside there is linear. So that makes them candidates for RCR. If your substitution is linear, we just integrate as normal and then divide instead of multiply by the derivative of whatever it is, the angle, the exponent, or the inside. So here, when you integrate sine, so we're sort of integrating the outer function, which is sine, that's negative cosine. So that's negative cosine of the same angle. So there's the antiderivative for the outer. And then what's the derivative of the angle? The derivative is 3. So if we were differentiating, we would do a multiplication by 3. But we are integrating, so we do a division by 3. So that just goes right out in front. I'll write that as a negative 1/3. And we're doing an indefinite integral, so we should have a plus c. Okay? And if we did this with traditional substitution, we'd have like 3 or 4 extra steps in there, which is why we like doing RCR. One of the things you want to do on exam is you want to be efficient. So if we can cut out a bunch of steps that really aren't valuable, let's do it. Here, we have an exponential. The antiderivative for an exponential begins with itself. And then we look at the exponent. Derivative of the exponent is -2. If we were differentiating, we would multiply by -2, but we are integrating, so we are going to divide by -2. That will be our antiderivative. Our general antiderivative.
Equally, you could also say -1/2
Yep.
to the negative.
Yep, we could also write that as -1/2 times e to the -2x. Yeah. Either, yeah, it's kind of, we have so many different ways to write the same thing. Bless you. Okay, over here, a little bit more complicated. And for many, it's helpful to write this as a rational exponent problem first. Do you want to close that door for me? Thank you. The power rule is what we are going to use here. Anytime we have like a power of x, we add the 1, divide by the new exponent. That's the power rule for integration. And that's what we do here. Right? The substitution we could use, u equals 4x minus 1. Could go that way. But this is linear, so we're just going to add 1 to the exponent. So we get 3/2. Divide by 3/2. That gives us 2/3. So that's the power rule part of it. If you're integrating x squared, you get x cubed divided by 3. So same thing here. Add 1, divide. But then we look to the inside, and the inside has a derivative of 4. If we were differentiating, we would multiply by that 4. But we are integrating, so we divide by that 4. So I'm just going to write it like this for a moment, and then we'll simplify it and write this as -1/8 e to the negative 2. Yeah, thank you. Yeah. Yep, thank you. I started realizing it just as I was writing. So that's going to be 2/3 divided by 4. We can cancel. You can think of it dividing by 4, multiplying by a 4th, however you want to think of that. And so we get 1/6. All right, so that's kind of the RCR thing. I will be using that from here on out. You can always do the traditional substitution also as a check, but you want to get in the habit of using RCR when the substitution is linear. And we'll have another example of this on the next slide. Or soon we will have it. Yeah, we can do RCR right here because that's a linear function in there. Okay, position from velocity. Now we can do what I was inclined to do with a couple slides ago. Here, notice that we still want to find position, but notice that, now we're given the initial position. So now we can actually completely find S of t. So there are two things here. One says determine the position function using the antiderivative method. And the other one is using the FTC, the fundamental theorem of calculus. So there is a difference. This is the preferred method. This is the method you did learn in Calc 1. I'll do one example with that, and it doesn't matter on the exam. If you do a method that works, that's great. But going forward, after I do one example of it this way, I'm going to stick to this way, because this way is a better way that's more transferable to other situations when you're not just dealing with position, velocity, and acceleration. It generalizes to all sorts of population models and applications in physics and chemistry and all over the place. So it's usually the better model is to understand the FTC method instead of the antiderivative method. But we'll do the first one with that method, just as a reminder, because you did see it in Calc 1. So the idea here is that we can integrate the velocity to get to position, and we can just do it generally. So if we say S of t is going to be the integral of the velocity with respect to t, and don't put any limits of integration. So if we don't put any limits of integration, we do this, then S of t is going to be the integral of sine is negative cosine plus c. And then we have to resolve the c. And so the way we resolve the c is with this initial condition. This says that when time is 0, the position is 1. So when time is 0, so we're going to plug in t equals 0. So let me change the color just so we're going to plug in t equals 0. So s of 0 is going to equal minus cosine of 0 plus c. Well, s of 0 is 1. That's given to be 1. Cosine of 0, unit circle, 0 degrees or 0 radians. Cosine is the first coordinate. That's 1. Then we isolate c, and we get that c is 2. So therefore, our final answer, s of t, so therefore s of t is going to be negative cosine of t plus 2. So this is how we would do it using the antiderivative method. So that is the antiderivative method. Is there any question on any of the steps there? So we're doing an indefinite integral, which leads us to a constant of integration. And then we take our initial value, s of 0, that's given to be 1, so we replace that with 1. Replace that t with a 0. Cosine of 0 is 1, so then solve for c. Now, if we do it the other way, the preferred way, if we do it with the fundamental theorem of calculus technique, here's what that would look like. So let's put a line there. So we would say that s of t is equal to s of 0. So that's the initial point. So s of 0 is the starting position, initial position. And then we're going to displace on the time interval 0 to t the velocity function. But we have to be a little careful here because we've already used t, so we're going to change the dummy variable to an x. We don't want to have a t as the variable and as the dummy variable. So we just replace the t with an x, or whatever your favorite letter is. If you like Greek letters better, you can use Greek letters. Your choice. And then we just do it, it's one line. You don't have this back substituting thing. It's just direct. S of 0 is 1. The integral of sine is negative cosine, evaluated on the interval 0 to t. So we end up with 1. So this is going to be minus cosine of t. And here we have to be a little careful. The antiderivative is negative cosine of x. So if we plug in a t, we get negative cosine of t. This part is not part of the antiderivative. So this is the antiderivative right here. I'll put it in purple. So we're plugging t in there. We get negative cosine of t. And then we subtract off what's inside the purple parentheses evaluated at 0. So we subtract off. We plug in 0. Cosine of 0 is 1. So we're subtracting off negative 1. So then we end up with 2 minus cosine of t. We'll have to remind ourselves how to do that whole antiderivative thing. Just remember that whatever the antiderivative is, you plug the upper limit into that antiderivative, and then you subtract off the lower limit plugged into that. So you get the minus 1.
Is that 2 minus cosine t?
Yes. So same answer, more direct. All right, we're just going whoop, straight through. All right, let's try this one. So S of t. So S of t is telling us the position at a future time. Right? That's what this is. And that's a lot of what we do in upper level math, is trying to build functions that model future behavior, which is a very important thing. That's how you make money in the world. If you can predict what something's going to do, that's how you make money. It's how all these engineering companies make money. They make predictions. And if you go on in engineering, you're going to end up taking a differential equations course. That's probably the most applicable skill imaginable. Because you go out, you have scientists that are going out and grabbing data from the real world that builds a differential equation, and then the math people solve the differential equation to predict what's going to happen from that data set. So predicting is a very, very basic thing that you do when you go on in math. So this future position is going to be wherever it starts, that's the initial position, plus the displacement over the time interval. So the time interval here, we're going to go 0 to t. And we can think of this t as any t value in between here, 0 and 4. Now we could also, let me just point out, that if we wanted to, well, this one doesn't give us a full time interval. Here, though, 0 to 4, there's two questions. You could be asked, what is the total displacement from 0 to 4? That's different than building this function. This function tells us where we are at any t value between 0 and 4. So the s of t is predicting where we are, but if we fix the interval from 0 to 4, you could integrate over that interval and get the displacement over that interval also. So in a lot of problems, they might just say t is greater than 0, or greater than or equal to 0, and not put an endpoint on it. Okay, so the displacement then, we put our velocity function here, but we have to remember that we've already used t, so I'll just switch it to an x. So the dummy variable is different than the variable. And then we're told that s of 0 is 1, so that's the initial position. Imagine our ball sitting at 1 on the number line. And then this is going to be the displacement from 0 to t. And this is going to be a function, right? Because we got a t up there. It's not a number. It's a function. So we are going to get negative 3 cosine of pi x. So the 3 just comes down. 3 is a multiplier. The integral of sine is negative cosine. Angle can't change. When you integrate or differentiate, the angle stays the same. But this angle is not just x, so we have to modify it. So we have to use the reverse chain rule. The derivative of the angle is pi. We need to divide by pi. So there's our antiderivative. This is evaluated on the interval 0 to t. And I'll highlight that the antiderivative is that. The 1 is not part of the antiderivative. So then we do our substitution. So now we plug in t, we get minus 3 over pi times cosine of pi times t. So that's the antiderivative at the upper. Now we subtract off the antiderivative at the lower. Antiderivative at the lower is negative 3 over pi times cosine of 0. Cosine of 0 is 1. I'm going to put the constants out in front here. So we're going to have 1. This is going to turn into a positive 3 over pi. So 1 plus 3 over pi. And then I'll put the variable here. So this is our function that's predicting the position at time t, where t is some number between 0 and 4. Now, if we wanted the total displacement on this interval, there's two ways we could do it. If we just do this, the integral of this function from 0 to 4, that'll give us our total displacement. Or we could figure out the position at time 4. The position at time 4, we would just plug 4 in right here. And what is cosine of 4 pi?
1.
And if that's 1, you get 3 over pi minus 3 over pi. So you get this. 3 over pi minus 3 over pi is 0. So if you cosine of 4 pi is 1. So 3 over pi minus 3 over pi is 0. So you get 1. So what is the total displacement then?
1. Nothing. 0.
0. Because this found our position at time 4. What was our position at time 0? 1. So the position at time 0 is 1, and the position at time 4 is 1. So we would end up with a total displacement. So if we were asked for the total displacement here, we would end up with 0. So that's what we should get. If we just integrate this function here from 0 to 4 directly, we will get 0. Displacement over the interval is the antiderivative of velocity evaluated from 0 to 4. So it's the position at 4 minus the position at 0. Position of 0 is 1, position at 4 is 1, so we get 0. All right, let's up the ante a little bit, and let's include acceleration. So as you've learned in Calc 1 and possibly physics, if you integrate position, I said that backwards. If you integrate velocity, you get to position, right? If you integrate acceleration, you get to velocity. So the order, if we start with acceleration, then velocity, so this is acceleration, then velocity is going to be the integral of acceleration with respect to time, and then position is the integral of velocity with respect to time. So that's our order. You could also say that S prime is equal to velocity and S double prime is equal to acceleration if S is position. So that's the order that we're going to go. Integrate one direction, differentiate the other direction. If you think about acceleration due to gravity being 9.8 or 32, acceleration is the constant. And so if you integrate the constant, you get to velocity, and you integrate again, you get to position. So you can think, somehow you have to just remember which way you're integrating and which way you're differentiating. Okay, so we can do the same thing. If we're given the acceleration function, we can integrate it on the interval 0 to t, and that is, we use the word displacement when we have a change in position. We don't have a comparable word here. We would just say the change in velocity. We don't have a single word that, like displacement means the change in position. We don't have a word that means the change in velocity, so we just say change in velocity. So same idea though, if we know the initial velocity and then we know the change in velocity, if we add the two together, we will get the velocity function. All right. And then here's how it all generalizes. So if Q is just some quantity like population, or it could be, there's financial applications, there's population lots of applications. But the idea is that the future population or the future value of some account will be the initial value of the account or the initial population plus the change in the whatever the Q is representing, population or change in the value. So same idea, same thing we just did, except instead of having an S, instead of having S's and V's, we're going to have Q's. But same idea. So let's try one. So generalizing, let's first do acceleration. So we all know this one. Acceleration is negative 32. So velocity at time t, the velocity at time t is going to be the initial velocity plus the change in velocity. And the change in velocity is found by integrating acceleration, just like the change in position is found by integrating velocity, just one step removed. So we're going to integrate negative 32 dt, and I don't want that to be a dt, I want that to be a dx. I want that to be a dx because I already used the t as a limit of integration, so we'll put an x. So that'll be the future velocity. We've got the initial velocity, and then there's some change in velocity, which we find by integrating acceleration, and that will give us our velocity function. Okay, so v of 0 is given to be 50. And then we integrate negative 32. Oh, that's easy. That's just negative 32x from 0 to t. Integrating a constant, we just add the independent variable, the dummy variable. And then, again, the 50 is not part of the antiderivative. The antiderivative is just the negative 32x. So the 50 is in front. And then we're integrating this. So plug in the t, and we get negative 32t. And then we subtract off the antiderivative at 0. So we're subtracting a negative. It's not going to matter, but it's going to be negative, negative 0. So we're going to end up with this as our velocity function. There it is, velocity function. All right, any question on any of those steps?
I'm just gonna catch up.
And then what do you think we're going to do to get to position?
Same thing over?
Do it again. Integrate again. So position, future position, will be whatever the initial position is, plus the change in position, aka displacement. And we get displacement by integrating the velocity function. Oh, but we already used the t, so we need to convert it to an x just because. We don't want our variables to be confused. So if we use t for the limit of integration, we want to use x for the, or whatever your favorite letter is for the integration variable. Now, s of 0 is given to be 0. So that's from up here. That's from given. And now we have to integrate this. So integrating a constant, we get 50 times the variable x. And then we integrate negative 32x, so that's negative 16x squared. We add 1 to the exponent divided by the new exponent. And that's from 0 to t. We only plug the 0 and the t into the antiderivative, which is that. So we're going to end up with 50 times t minus 16 times t squared. When we plug in 0 here, what do we end up with?
0.
0, so we don't have to put a constant. You don't have to write plus 0. Leave it like that. Any question on that?
So, maybe this is a dumb question.
That's okay. I love dumb questions because I can answer them usually.
Yeah, so I get where the S0 goes to 0. That was like just a given.
It's given, yes. S of 0 is given.
And then you have the, you have that, I guess you call that integration with the t to 0 to t right there, 50 minus 32x. And okay, so you got to integrate that, and you get 50x, and then negative 16x.
Because we add 1 and get a 2, divide by the 2.
Okay.
Yep.
So
You see it?
I think I'm.
You didn't even ask a question.
I like this whole first half of this class. I've just been totally lost, and now I think I'm starting to
Get oriented?
I think so. Yeah.
Well, let's see if you're oriented. Do the next one. All right, you all try the next one. Let's see. Let's see if we're crashing and burning or if we're emerging from the ashes after an hour of integration. Has anything sunk in yet? Yeah, so give this one a try. And so you should be able to model it right after the one above it. Let me know if you have a question. I'll give you a nudge if you need it. Yeah, you talked your way through that one perfectly.
Yeah, so S is just like a fixed position.
Well, S is, if you look, we're creating a function though, right? So S of 0 is a fixed position. So
Okay.
S
S
evaluated
of a value
is a fixed position.
Okay.
But we're finding S of t, so we're finding
Okay.
S of a function.
Okay.
So a function of t.
Okay. T. Yeah. T can
T
be
is,
any
the
number.
yeah, t is going to be the independent variable
Yeah.
from whatever interval or
Right.
that we're looking at. So then the only issue, we don't want those to match. So we'll change the dummy variable, we'll swap it over to an x or or a theta, or an alpha, or a zeta, or a beta. Oh, is read only, okay. Yeah, that's pretty nice though, it just comes up live in there. You don't have to. Is it pretty responsive, or coming up pretty
Yeah.
quickly?
I think if I let it turn on, then I have to I refresh, but that's
Mhm.
fine.
Gotcha, yeah. So v of t, we want the velocity as a function of t. That means we first need to know what's the initial velocity. We want to find the future velocity. The idea is find the initial velocity and then add a change in velocity. And the change in velocity is the integral of acceleration. And I'm going to switch the t in the acceleration function to an x for that integration step. So v of 0 is 60, that's given. And then we integrate, okay, let's be careful. The integral of an exponential is itself. But then we look in the exponent position. The derivative of the exponent is -1, so we divide by -1. So this is going to make it 60 minus e to the negative x. And that's evaluated from 0 to t. So then we're going to have 60 minus e to the minus t. And then what goes here?
Plus 1.
Plus 1. Do we see it? So
Where's the plus 1 come from?
So there is the antiderivative.
Okay.
So we plug in the upper limit and get this piece. And then we subtract off purple at the lower limit of integration. Plugging in the lower limit of integration, we get e to the 0, which is 1. So we have a -1 as the lower limit evaluation, but we're subtracting off the lower limit. So we're subtracting off. So in our mind, we have to remember that it's minus minus 1. So we'll end up with 61 minus e to the negative t. So that is definitely the trickiest little piece there. You just have to remember that this whole quantity, you plug in the t, that part's easy. When you plug in the 0, you get -1. But the whole process of evaluating a definite integral, you do the upper limit minus the lower limit. So if the lower limit happens to be negative, you're subtracting a negative, which makes it a positive. Very easy to get tangled up there. Okay, so let's now find the position as a function of t. So the future position, you're imagining t being in the future position is the initial position plus the change in position, aka displacement. So 0 to t, we integrate velocity. Velocity is what changes position. Right? That's how the position is changed. Velocity moves the thing. So if we integrate velocity, we'll figure out how far it moved it. So there's our setup. S of 0 is given to be 40. We need to know where we're starting. Now we're going to integrate term by term. So that integrand has two terms. We just integrate term by term. The integral of 61 is 61x. And the integral here is going to be plus e to the negative x. So the integral of e to the negative x is e to the negative x divided by -1. When you divide -1 into this negative, it becomes a positive. And that is evaluated on the interval 0 to t. Once again, the antiderivative piece is right here. So the t and the 0 aren't being plugged into the 40. 40 is separate. This will give us 40 plus 61t plus e to the negative t minus, so here is the antiderivative at the upper limit. And then over here is going to be the antiderivative at the lower limit. So we plug it in. We're subtracting off 0 plus 1. So when all is said and done, So does everybody agree? And I'm going to put parentheses right here. So this is the antiderivative, and if we plug in 0, we get 0 there. We get 1 there, so we have 0 plus 1, but that's the whole antiderivative. At the lower limit of integration, that's all being subtracted off. And then we end up with a final answer of 39 plus 61t plus e to the neg t. So that is our future position. The moon. Or beyond. Bless you. All right. Any questions on any of the steps there? So moral of the story right now is practice those integration skills. Get in my math lab, do a bunch of integration skills, because it's very easy to get tangled up. And none of this is hard, but there are definitely some subtleties that you want to practice with the subtraction in particular. So let's do one where we aren't dealing with SVA. So we've got a population that we are going to be analyzing. And that is the change in population as a function of t. So scientists can go out and measure how fast the foxes are multiplying. Build a function. Now we got to do math on it. So we want to find the population in the future. If they're multiplying at this rate, what's going to happen in the future? Obviously, population models get way more complex when you start putting in the variables that we know are there that aren't in this equation. This is if they're multiplying in in an ideal environment where there's not wolves and all that other stuff. And as you get into higher level differential equations classes, you start to put those extra variables in. So there is our rate of change, population change. So P of t, population in the future, is going to be the population that we start with when we start our measurements. So P of 0 plus the change in the population, which is sort of analogous to displacement. So we're going to integrate the rate of change function. And I'm going to rewrite this angle just to hopefully be suggestive. So the angle, I'm going to write it as pi over 5 times t. That's a linear function. Power on t is 1. dt. We don't want t, so we're going to switch that to x. So make that an x, make that an x, and we're going to go 0 to t. There we go. So that is our future population of foxes if wolves are imaginary. So then P of t, P of 0, we're told that we're starting with 35. And now we have to integrate this whole thing. Again, it's 2 terms, so we integrate term by term. Integral of 5 is just 5x. So 5x. Integral, so constants just come along for the ride, little constant multipliers. So integral of sine, we've already talked about. We've done so many signs already. Integral of sine is negative cosine. So we're going to have negative 10 cosine of the same angle. Angle does not change when you integrate or differentiate. Okay. But that angle is not just an x. It has a derivative of pi over 5. It's a linear function. The derivative of a line is its slope. So the derivative of this is pi fifths. We divide by pi over 5, which will mean multiply by 5 over pi. But I'll write it first as division by pi fifths. And then this is evaluated 0 to t. All right. So our P of t, if we simplify this, we're going to have 35 plus, t goes in, And once again, the antiderivative is all of that. So the t goes in and we get 5t minus, dividing here, remember, becomes multiplication, so it's going to be 50 over pi, so minus 50 divided by pi, times the cosine of pi over 5 times x. That's the angle. So there is the antiderivative at upper. And then we subtract off antiderivative at lower. So the antiderivative at the lower is going to go in there. So the antiderivative at 0, we're going to have a 0 right there. And then minus, this is still 50 over pi. Same as it was over here. But then this is going to be cosine of 0. Cosine of 0. Visualize your unit circle, 0 degrees, 0 radians. We're over on the right. Cosine is the first coordinate. Alphabetical order, right? C comma S. C for cosine is associated with x. S for sine is associated with y. Alphabetical order, C comma S. And our final step, we are going to have 35. This, oh, I have a x in here. What should that be?
T.
That should be a t, thank you. That should be a t in here because we substituted this t in for those x's. All right, so 35 plus 5t. Yeah, this part's not changing. And then we just said cosine of 0 is 1, but we're subtracting a negative, so that becomes 50 over pi positive. So there is our population of foxes in the future. So the second part of the question says, what is the population 15 years out? What's the population 35 years out? So P of 15, once we have this model, then we're just plugging in the 15. So we plug in the 15, we're going to get an approximation. 15 times 5. Plug in the 5 here. What is cosine of pi? So if we plug in 15 here, we have 15 divided by 5, which is 3. So we have cosine of 3 pi, which is the same thing as cosine of pi. You subtract off 2 pi. So cosine of pi, cosine of 3 pi is negative 1. That negative is going to multiply in front and make this positive. And then we, let's see, there's no variable over there, so we have 50 over pi is just coming along as an addition. Not much we can do here. We can combine these two numbers and get a $1.10. Add these and we get 100 over pi. And of course, we're talking about foxes. So if we type this into our calculator, we can get an approximation and just round it up to the nearest fox. Get an approximation. So if you type it into your calculator, you can get an approximation, whatever that might be. And what would we do if we plug in 35?
Same thing.
Same thing. Plug in the 35 for that t, plug in the 35 for that t. Here we're going to get 7 pi, which again is going to have a cosine value of negative 1, so it's going to look really similar. The part that's going to be different would be this part, the 5t. But you would do the same thing. Make sense? Feels good to be doing math after a month of just being lazy. Golly. We're so lucky we get to do this. We could be doing laundry in a creek. So this just summarizes all the stuff. This is for the traditional application that you first are introduced to it through, the physics application, position, velocity, acceleration. And then this is the generalization that you'll see in economics classes, physics classes, wherever. All right, section 2. Geometry, Riemann sums. Did I hear a groan? Riemann sums, it's like the thing. That's what allows us to find area. It's crazy that you just integrate the difference of the curves and you get the area between them. Okay, now I mean, imagine being that dude that figured that out. It's like, oh, if I just add 1 to the exponent and divide by the new exponent, I get the area beneath the curve. That was a little mind-blowing. That's like ultimate. All right, so the idea here is that in this class, we're not going to do Riemann sums the way you did them in Calc 1, the way that you sort of suffered through left endpoints, right endpoints, midpoint. We're not doing any of that. But we're using the concept a lot. So the concept is that if we partition this region, we have a bunch of rectangles, and we know that the area of a rectangle is base times height. And the idea is that we shrink the width of each rectangle so that we increase the number of rectangles, which improves the approximation. And then the magic bullet is you integrate that. The Riemann sum is an approximation. But if you take the limit and let the number of rectangles go to infinity, the Riemann sum becomes an integral. So that's sort of the pivotal, that's the crux. And so that's what this is just sort of describing. Okay, we've got the width of these rectangles. B minus A over n is how wide each rectangle is. If we let the number of rectangles go to infinity, the width of the rectangles is going to 0. So then we're just going to figure out that the height of a rectangle is the upper function minus the lower function. If you have a vertical distance, the way you find that distance is take upper minus lower. If you have a horizontal distance, you take right minus left. So we're just taking the difference to get the height. So the height is f minus g. The star value is just an x value that's in that interval there. And then the delta x is the width of the rectangle. So that's the Riemann sum right there. And then we take the limit as n goes to infinity. That's where we sprinkle our fairy dust. And we end up with this simple math statement that the area on the interval a to b, you've got two functions that are not intersecting. F's above g, upper minus lower. That's the area between them. All right. Okay, so if we look at those two functions here, I put the upper function in black, the lower function in red. In this scenario where we're using the x-axis as the upper function, so that upper function is y equals 0, or if you use the f and the g, then f of x is 0, and g is the lower function. All right, so we are going to call this, so if we are integrating here, I'm going to call this, I'm going to draw a representative rectangle. Sometimes it's referred to as a representative element. We have to decide if it's going to be if the rectangles are standing or if they're sleeping. So in this case where we have an upper and a lower function, we have vertical rectangles. If we had curves that were oriented this way, we would have horizontal rectangles. So here I'm going to draw a representative rectangle. That's a terrible rectangle. Let's use a different color. Let's use this orange maybe. I know. So this is just a representative rectangle at a random x value. So this is a random x value right there. So you're imagining that rectangle having a thickness of dx. Right? So the width, that thickness is dx. And then the height of this rectangle, so from here to here, is whatever the function value is up there minus whatever the function value is down there. Upper minus lower is going to give you the height. And so when we go to find our area, the area between these curves is going to be the integral from that intersection point to this intersection point. So we definitely need to figure out what this b is right there, and that a appears to be 0. But that's going to be our interval. We'll find those in 1 minute. So upper function, negative x squared plus 4x, minus the lower function, multiplied by dx. So when we're thinking Riemann sum, this right here is the height. This right here is the width. So that gives us the area of a rectangle. And the integration symbol looks like an S because it is. It's summing up all those rectangle areas to get a total area. So this sums up all these little areas to get a total area. And let's see what our limits of integration are.
Is it supposed to be x squared plus 4x?
Let's see, the upper function is x squared plus 4x. Thank you. Yes, thank you. And then, so that function minus that function. Good. Good eyes. All right, so it appears that the left endpoint is 0, the left intersection point. But we don't know that for sure until we do a little bit of math. How do we figure out these two intersection points? So if we want to find those 2 points, what are we going to do with the functions? Yeah, create a system, set them equal to each other. Yep. So if we set them equal to each other, we're going to have negative x squared plus 4 times x equals x squared minus 2x. Nonlinear. Your strategy from algebra, nonlinear. Everything to one side equals 0 and then factor. So we put everything on one side. Doesn't matter which side. I'm going to go to the right because that makes it positive for the leading term. So we get that. There is a GCF here. So we get that. And then we notice that we've got 2 x values that make that true, 0 and 3. So those have to be the x values of those intersection points. A has to be 0, B has to be 3. So that tells us that our integration is going to go from 0 to 3. That make sense? Now we have to simplify our integrand here. So we're integrating from 0 to 3. This is going to be negative 2x squared. 4x minus a minus is plus 6x dx. So we'll get negative 2/3 x to the 3 plus, add 1, we get 2. Divide by 2, we get 3. And that's going to go 0 to 3. Plugging in the 3, we're going to get 27 over 3, which is 9. So we get negative 18 plus 3 times 3 is 9 times 3 is 27. So it looks like 9. Plugging in 0 gives 0. So that will be the number of square units between those two curves. It's an integer. If you looked at that, you would never guess that that area is an integer. I wouldn't. Maybe you would. I don't know. I wouldn't. It looks more complicated than an integer, that curved area. All right. Any steps of the integration that you have a question on?
So from 0 to 3 with dx at the end, and then the next step, that's just the derivative, right?
This in here is the upper function minus the lower function.
Yep, and then that.
And then this is simplified, and then this is the integral.
Integral.
So let's take a look at the one here. So same idea. We're going to draw a representative rectangle, a representative integration element. And when you draw an integration element, you have it at a random x if your integration rectangle or element is vertical. If it's horizontal, it's at a random y. So that little x is just the random x. And so then that x moves through the interval from 0 to whatever that is. All right, so it's the same idea. You're in your mind, you're imagining this element sliding through this whole area, creating all those little rectangles, and then we're adding them all up. So in this particular case, our area is the integral from, it appears to be 0 to something, but let's just get those in a second. So it's the upper function. The upper function here is 0. So that's going to start with a 0 minus the lower function is this wacky looking thing. So we'll just put it as it is for a moment. So that right there is the height of a rectangle. That's the height of the rectangle at x. And then we have our integration differential, so dx. And then we have to figure out our limits of integration. Okay. Setting these equal to 0 is not too complicated because one of them is 0. So we have that. So the only way that you can multiply two things and get 0 is if one of those things is 0. So this tells us that cosine of x is 2 or sine of x is 0. All right, now we're talking trig. I dare you to give me an x value that has a cosine value of 2. I'll give you money if you can give me an x value that has cosine value of 2. Can anyone come up with an x value? Cosine value of 2? Why not?
Doesn't exist.
Doesn't exist. It's outside the unit circle. Right? When you have a unit circle, cosine can only go from -1 to 1. Sine can only go -1 to 1. So cosine x equals 2 is unsolvable. All right, so that, no solution. So that part has no solution. And now over here we have sine of x equal to 0. In your mind, you should be thinking unit circle. And on the unit circle, sine is the second coordinate. So the places where sine is 0 are at the east and west sides of that circle. So 0, and then pi, and then 2 pi, and then 3 pi, and then 4 pi, and then 5 pi, and then 6 pi, and then negatives also. But when we look at this picture, it's pretty clear that we just are looking for the very first two starting at 0. So this tells us that x is going to be 0 or pi. We're not going to go beyond that. Because the curve doesn't, it's going to oscillate and come back down, but we don't care about that. We're looking at the first two zeros. So integrate from 0 to pi. That'll be our jam. Okay. You have to do a little bit of work here. So we don't know how to integrate multiplication at this stage. Unless you can see a way to use substitution that might cut to the chase. So substitution is the only more complex technique you have at this stage. So if I said you could integrate this, it would have to be with substitution, because that's the only more complicated technique that you know. I'm going to rewrite this one step. This minus sign, I could distribute it in here, and that would be equal. If I distribute it in, I'm going to get 2 minus cosine of x if I switch the orders, just so that the subtraction is not leading. Everyone agree with that? Distribute the minus in. What is the derivative of 2 minus cosine x? What was that? Sine x. Bingo! So if we let u equal 2 minus cosine x, so this is not an RCR. Right? It's not an RCR. The substitution's not linear. But what we notice is that, oh gosh, if we take the derivative of this, we get sine of x dx. So this whole integral can be rewritten as u du. Now these are not u limits here. I'm going to just put placeholders here for a second. You could find new limits if you wanted. I don't want to because we don't have a ton of time. And then this integrates to 1/2 u squared between these placeholder limits, which we don't care about because we're just going to jump back to u. We're going to jump back through this u to get back to x. And if we go back to x, then we go back to our x limits. So we replaced this with u. We replaced that with du. The integral of u is u squared over 2. And then we replace the u back to the x's. Now we just evaluate. If you plug in pi right there, so we have 1/2 2 minus, what's cosine of pi? -1. Cosine pi, -1. So that's -1, so that's going to be +1. All right. And then I need to subtract off. When we plug in 0 in here, what do we get? So if we plug in 0, we still get the 2. We still get the minus. Cosine of 0 is 1. So we get that. So here is the upper evaluation. Here is the lower evaluation. We take the difference. 2 minus 1 is 1. 1 minus 1 is 0. We end up with 1. If you do that algebra.
Where did from the half you squared, what happened to the squared?
That is a very good question. I was rushing. Dang it. Good point. Let me put these parentheses in and put squares on them. Would that make sense then? So we have the half out in front, and then this is going to be 2 minus minus 1 squared, and then we're going to subtract off 2 minus 1 squared. So that's going to change this number. That's going to be 3 squared, which is 9, and that's 1, so that's going to be 4 then. Do you agree with that? Good call, because that area is definitely more than 1. Do we agree with that? So this is our antiderivative, and it has to be squared because it's u squared. So plug in the pi, square it, plug in the 0, square it, take the difference, and then multiply by half. I'll double check it right now since time is up. I think that's right. Thank you for noticing. The little things. All right, well, welcome to spring semester 2026. You get started on your My Math Lab. Get into OneNote. If you have any issues clicking that link, send me an email. We'll figure it out. It generally works really well. Make sure you open it in the app. And don't just use it in the web browser. It's way better in the app. Yeah. I will see you all Thursday. Thanks for coming.
Thanks, man.
Okay,
Good.
before you take the board down, I got